All right, next up in section 13.4, we'll look at question number 6. This says that the mass density measured in kilograms per cubic centimeter at the point xyz is given by the function, so this is a rho, R-H-O, it's a Greek letter, rho of xyz is equal to 4 divided by the square root of x squared plus y squared plus z squared. So notice here this is a function of 3 variables. Our job is to compute the derivatives partial rho partial x, partial rho partial y, and partial rho partial z. Then it asks us to compute the derivative partial rho partial z, and this just means evaluated at the point 236 and interpret our result. Okay, so here the setup is that as we move around in space, right, so if I'm going to say located at the point xyz, the mass density at that location is given by this function rho. Okay, so we're going to go ahead and first just compute the first order partial derivatives, and for a function of 3 variables the idea is exactly the same. So if I want to say compute partial rho partial x, okay, here I'm just going to hold both y and z constant. So here we just hold now y and z constant, and we're letting just x vary, okay? And I'm differentiating this function here, and notice I'll go ahead and rewrite this for simplicity of derivatives here. This is going to be 4 times the quantity x squared plus y squared plus z squared to the negative 1/2 power. Okay, so now to compute the derivative of this thing, what we're going to do is just apply first the power rule, so the negative 1/2 will come down. That's going to give us a negative 2. Then I'm going to get x squared plus y squared plus z squared to the, well, I have to subtract 1 from this exponent, so minus 1/2 minus 1 would be minus 3/2. And then from the chain rule, I have to multiply by the derivative of what's inside with respect to x. And since y and z now are held constant, that's just going to give us a 2x. Okay, so then putting this all together, I'm going to get a minus 4, right, because of the 2 and the 2, so minus 4x, and then I'm dividing that by the quantity x squared plus y squared plus z squared raised to the 3/2 power. Okay, so this would be our x derivative. Now, the y and the z derivative, what are those going to be? Well, since our equation for the density is so nicely symmetric, right? The roles of y and x and z, right? They're all basically playing the same role. So if I think about what the y derivative would look like, it's going to look exactly the same as this, right? Differentiating this with respect to y would be exactly this, except for the chain rule factor. And what would that be for the y derivative? It would simply be 2y instead of a 2x. So putting that all together, really all I need to do is swap out the roles of x and y. And so I would get this, just taking advantage of the symmetry there in our expression for the density. So this y derivative and in fact the z derivative, these are kind of freebies because of that symmetry. So this would be minus 4z divided by x squared plus y squared plus z squared to the 3/2. Okay, great. So these are our derivatives. Okay, and in terms of interpreting what exactly it is they're measuring, right? Well, each one of these is telling us a rate of change. In this case, it's telling us the rate at which our mass density changes in the principal directions x, y, and z. So the x derivative here, this expression, if I plugged in some coordinates, that would tell me the rate at which the mass density was, say, increasing or potentially decreasing as I move in the positive x direction, okay? And then likewise for y and z. Okay, so now let's go ahead, I'll get rid of that. Let's go ahead now and look at the derivative for z evaluated at 2, 3, 6. Okay, so here I'll just first, oh, that's a d, not a del, so this is, and then I want to evaluate this at 2, 3, 6. Okay, so what that means is I'm going to take my z derivative that I just computed, and then I'm just going to plug in, oh, sorry about that, I'm going to plug in the coordinates to this expression. So this thing gets evaluated at 2, 3, 6. So this would be what? Well, z is 6. That'd be a minus 24 up top. And then on bottom, I'm going to have what? Well, 2 squared plus 3 squared plus 6 squared all to the 3/2. Okay, now you can check here, 2 squared plus 3 squared plus 6 squared is 49, okay? And so then if I do 49 to the 3/2 power, that's going to be 7 cubed, also known as 343, okay? So this would be my z derivative evaluated at 2, 3, 6. And so as far as the interpretation, okay, this would be saying what? Well, our derivative at 2, 3, 6 is this negative 24 over 343. Now the units here, right? Rho is measured in, we said, kilograms per cubic centimeter. And then this is a rate, right? So it's the change in that density per unit change in the z direction, and z is measured in centimeters. So it'd be kilograms per cubic centimeter per, right, centimeter change in z. Okay, so we're saying at that point the mass density here is decreasing at this particular rate as we move in the positive z direction. So if we were here located at 2, 3, 6, if I were to move vertically upward in the positive z direction, my density would be going down. Okay, that's going to do it for this problem.